the whole talk will be about chaotic systems. So I will talk about our recent work. It's basically how we can think about adiabatic flows in the Hamiltonian spaces. And mostly it was done by Tolle and then two gentlemen on top, Peter and Shaw. I only showed photographs of junior people because Tolle is sufficiently famous already. And there was a related work involved with other students and postdocs, which I'll mention also. So I'll start from introduction, and maybe some of you know already this stuff, I heard this stuff. I'll try to make it as concise as I can, but it will still take me some time. And let me just kind of allude to main themes of this talk. This work is still in progress, so as actually the last point here was also suggested by Tolle, so the conclusions kind of jump a bit, and this also correlates with random matrix theory. But I still thought it's kind of interesting. It looks like we are finding interesting results, and then I'll try to show them. So first of all, I will talk about a well-defined structure of adiabatic transformations in chaotic systems far from the ground state. We of course know that ground state is fine, we can transform it adiabatically, and I'm talking about high temperature states in chaotic systems where adiabatic theorem doesn't work in some sense. More than that, I will talk about even infinite temperature RG type adiabatic flows, in some sense flows of identity matrices. And it probably doesn't make sense now, but hopefully it will make sense later. So essentially, I will try to argue that we can understand a lot on the operator level. So we don't really need to talk about the states when we define these adiabatic transformations. And then we can apply them to states. And in particular, for ground states, of course, we will recover nice results. But a lot of what I'm going to talk is built into operator structure. So then we found some interesting side results that the object which I'm going to define, this generator of adiabatic transformations, can have singularities which could be removable, and this leads to interesting physics. So there are special states, if you want dark states in chaotic systems. There are lots of parallels with scars which people discuss now, but precise relation we don't understand right now. And then I'll talk also about at least one application of this idea. It's not just some abstract stuff. That you can go beyond if you want Schrieffer-Wolff transformation or do, and Schrieffer-Wolff transformation, I'll introduce it. It's a kind of attempt to block diagonalize your Hamiltonian. So if you want to derive your low energy theory, and then I'll show that we can do it variationally without perturbation theory, which usually diverges, gives you small denominators and so on. I think there should be applications to field theory. We discussed them, but we didn't do any work. So let me start from some introduction. So assume that we have some Hamiltonian, and we want to diagonalize it. So there is some unitary, which depends on some parameter, which could be multidimensional. So this is, if you want, our coupling. And our Hamiltonian depends on this coupling. So when we diagonalize it, we know we can always diagonalize it by unitary. So now I assume that it's all finite dimensional. I don't worry about cutoffs and so on. So, and in particular, the same unitary, of course, tells us how our eigenstates of this Hamiltonian depend on precisely what's done in the Schrieffer-Wolff transformation. Well, it's a partial diagonalization, but basically this standard notation, this unitary is e to the minus is, just to make connection with this part. So now we can just differentiate this equation on top. I'm sorry, I guess I messed up. I don't have any pointer. So top right. And this doesn't work, I was told, because I'm using my own computer. Anyway, so this equation on top, we just differentiate with respect to lambda, and then, well, it's a very simple result. And then if we differentiate, it's connection with Schrieffer-Wolff, it's not important. And if we differentiate the right-hand side, we also get a simple result, because our eigenstates here, they don't depend. We say a not, sorry, it should be a not. Anyway, they don't depend on lambda. So we get a diagonal matrix. And then you can just notice that commutator of this is equal to 0. Oh, this works. Okay, thank you. So, and this is basically an equation which defines what is this object gauge potential which diagonalizes Hamiltonian. So, occasionally in some slides you will see h bar. I just want to emphasize it's well defined in the classical limit. So there will be 1 over h bar here. So, and then this A plays the role of canonical generator of canonical transformations which diagonalize Hamiltonian. And this is also related to Wilson-Wagner flow equations. So, so this object, this generator of adiabatic transformation, AGP, adiabatic gauge potential, there was some uncertainty how to call it different places. This object is, of course, known. It appears under different names, sometimes connection or whatever, but at least Wikipedia says it's gauge potential, so we stuck with this term. So you can think about this as this derivative of the unitary. You can also think about this as derivative operator, like a momentum, in this sense that the action of gauge potential on eigenstates is exactly like action of derivative on the eigenstate. And this is also a solution of this equation. I'm sure this problem arises. So if you think about chaotic models, they satisfy ETH, which is basically a version of random matrix theory. And then we know that these off-diagonal elements are very small, and the scale is 1 over square root of Hilbert space size, so e to the minus entropy over 2. But denominator's scale is e to the minus entropy. So if you just look into the ratio, we just see that norm of this object is exponential. So it basically means that it's a non-local object. It doesn't exist. In a sense that I just add one particle to the system and it just changes completely. Think about this as a projection operator. So it's non-differentiable. It contains all possible non-local operators you can imagine. It's interesting that first person who kind of noticed it in the context of classical chaotic systems was Jarzynski back in 95. So there is a nice consequence of this, that if we have a gauge potential, then we have integrability. And it turns out it's not I'm going to mention here. Indeed, there are connections, direct connections between finding these objects or even definition of quantum integrability and finding this object. Well, I just play a few more games just to make connections of this adiabatic gauge potential with other things we know. So if you look into this expression which I wrote, then we can recognize that this is just time average of this operator propagated with the, so I take a conjugate force, so say magnetization if lambda is magnetic field, dress it with a Hamiltonian, propagate, and then do time averaging. So this is basically infinite time average, epsilon is regularization. So we see immediately that this exists grows, and this was studied by David and collaborators and many other people. So this is how we study how operators grow under the quadrant. So in particular, locality of adiabatic transformation, so the fact that this object is local, is tied to the fact that our operators don't grow. Then another thing which I mentioned, that once you know what these are, you start to see them literally everywhere. So I'll show a few more examples. I spent also one slide on geometry. It's very interesting in this context, and it's also tied to adiabatic transformations. So this is a same setup. We have a Hamiltonian which depends on some couplings, and then we define some manifolds of states which could be here could be, say, ground state or some eigenstates of the Hamiltonian. And we can ask how fast these states change if I change my parameter. So this is a natural way to define a distance. And if I look into overlap between these two states, so say ground state at parameter lambda and lambda plus delta lambda, it's kind of a very simple exercise to see that, well, because it's positive, it cannot have any cross terms. So it's given by this second order form, where this is positive definite tensor. And this is called geometric tensor, which was introduced by Provost and Wally. And if you look, it's nothing but overlap of derivatives of my wave functions. But I just told you that derivative is the gauge potential. So it's a covariance of the gauge potential. So what I told you before, so in particular, symmetric part defines the metric structure, and yeah. And what I told you before, that the norm of gauge potential diverges, is nothing but saying that the distance between wave functions changes like extremely fast. And this, we know it should happen in chaotic systems. So just last line, so if you, well, you all know Berry curvature, it's nothing but the expectation of the commutator of the gauge potential. So this appears in dynamical response and so on. One thing which I'm not going to talk about, but I think which is just interesting to mention, it turns out that added mass in the general setup is proportional to this metric tensor. It's kind of a very simple calculation. So mass we see, if I start moving a box, there is an extra added mass there, and it's really related to this metric part. So geometry is built inside quantum mechanics like very, very deeply.
Before that, you said that the spacing of levels in perturbation theory goes like e to the power minus s, and the perturbation like e to the power. Yeah, why is that?
So this is essentially a consequence of ETH, but simple derivation is very simple. So think about this. You compute variance of this operator in an eigenstate. And will be sum over all off-diagonal elements of this matrix element squared, sum over M. So one V fixed, one V sum. And we know that this variance by ETH, for example, should be given by microcanonical average. So for any physical operator, it's not exponential. It could be maybe extensive, maybe intensive. But now you see, ETH, or random matrix, tells us that all eigenstates are similar to each other, up to like smooth function. So density of states, you just substitute the sum by an integral.
Maybe not. You can have eigenstates, states that are ETH and other states that are perpendicular.
You can. Well, you are talking about mixed phase space now, so I think general believe that in generic chaotic systems, ETH works. Of course, if you deal with integrable systems, it becomes different.
That's not possible. They cannot be all perpendicular. If there's one ETH, there should be other one. Excited states can then not be ETH. The kind of state is.
Well, there are very special models which kind of show it, but I'm not talking about states close to the ground state or whatever. So there, of course, it's different. But in the middle of the spectrum, there are so many numerical examples now that ETH is like very reliable. But yeah, if ETH does not work, then this object is not exponentially big, and indeed, that's what I mentioned. If it's not exponentially big, we have some structure. Could be integral. Oh, entropy, sorry. It's 1 over, e to the minus s is 1 over Hilbert space size. Yeah, so this is 1. Okay, so this is geometry. So just maybe one of the last introductory slide. So it turns out that the same, like this object which defines adiabatic transformations, it also appears in dynamics, not necessarily adiabatic dynamics. And maybe the simplest way to see it is that let's imagine that we look into evolution of some state, could be an eigenstate, if our Hamiltonian is time dependent. Well, think about some moving boundary or something like that. So formally, I can go to a moving frame, and in quantum mechanics, it means that I apply this unitary transformation to the wave function, and then I look how this wave function depends on time, and then I will get two contributions. First, from the Hamiltonian, but second, because this unitary depends on my parameter, which depends on time. And then it's easy to see that my moving Hamiltonian up to this unitary dressings has this extra minus lambda dot A. And you see immediately, if A is small in some sense, or local, then this term is harmless. At least I can fight with it. It doesn't lead to dissipation. But if A is like terrible monster, then I have a hard time. So in some sense, we just see, and this is not just, I'm not discussing limit lambda dot goes to 0. So even if lambda dot goes to infinity, if A is local, I have very nice adiabatic transformations. Good. So just to maybe formalize it a bit and make connections, like interesting connections, which we still don't understand what it means, we can sort of define also time component of the metric, which is just distance, how distance between wave function grows in time. Well, and it's exactly the same expression, but you'll get derivative with respect to time. So what is derivative with respect to time? It's a Hamiltonian. So we see that energy variance has a meaning of actually metric with respect to time. And then in the leading order of adiabatic perturbation theory, we can just derive it. We see that it's proportional to square of velocity, how fast you change parameter, times this metric tensor. And this immediately quantifies what I said. So if this metric tensor is small, our energy variance is small, so we are very adiabatic, right? We can follow eigenstates very well. And it turns out that this is also related to speed limits and other things which I'm not going to talk. And the last thing I'll just mention for completeness, that it's relatively new development, that if we drive the system not with Hamiltonian H, but H plus lambda dot A, then in the moving frame our Hamiltonian is diagonal matrix, so we have no transitions. So this is what is known as counter-diabatic driving or transitionless driving. Now, how do we find these gauge potentials? Well, just said we need to solve this equation, but I already basically told that except for special models, this equation cannot be resolved. There is no solution. But then there is a very interesting or useful, I would say, relation that if we look into this equation, we can realize after, I guess, 2 lines that this is equivalent to minimization problem. So what I'm doing, I'm trying to find A, which minimizes square of this sum, trace of the square of this sum. Well, and if we have minimization, we can develop variational procedure. And then we can find what is the local gauge potentials, which maybe don't solve this equation, but make it as solvable as possible. And there is another connection with work which was done by David, and actually Peter found it's in footnote that basically they were using same constructions, that actually what we are doing by finding generator of adiabatic transformations, we are finding slowest operators. It's kind of was not immediately clear, you just see similar structures, but it's actually quite precise because we are defining this operator. What is this? It's a conjugate to this parameter, and then we try to apply local unitary rotation, which make it as diagonal as possible. But if we make it diagonal, it has infinite lifetime. It doesn't decay. So what we are trying to do is to find slow response to existence of good adiabatic transformations. All right. So I'm going back. So now we have variational principle. So the question, what is the good variational basis? So one can just use all possible operators, but complexity gets very big. And especially if we deal with unbounded local Hilbert spaces, it becomes like huge. So what do we do? Well, if you look again into this expression, then we can notice that we can just do cumulant expansion, just do Baker-Hausdorff formula. And we just realize that we get formally this A has a structure of this type. So we have our generalized force and commutators with H. So we actually create orthogonal operators in some sense with each other, at least orthogonal to the previous one. So, and if you spend a little bit more time, you will see that only odd powers will contribute. So, and this tells us that maybe if you are interested in this variational ansatz for this adiabatic gauge potential, again for Hamiltonian, which adiabatically moves out between these manifolds, then we can use this as a variational ansatz. And then there is another mathematical fact which Peter found, which I think is very curious, and yeah, I'll mention this later. So if you look into matrix element of exact gauge potential, we'll get this matrix elements of generalized force over energy denominator. And for variational, we'll get exactly same matrix elements, but then we have energy denominators in numerator. So in some sense, we are trying to do sort of a crazy thing. We want to approximate 1 over x as a polynomial. So that's really what variational ansatz is doing. And this looks a bit weird. But if you think about this, this makes perfect sense. And then if we look into numerics, like we just apply variational principle, that's exactly what's happening. So this is excitation frequency. Of course, in reality, we have discrete points, but if Hilbert space is big, it becomes a continuous line. And then we look into ratios of this matrix elements of this gauge potential over matrix elements of our conjugate force, and look into ratio. So exact result should be 1 over x, and there is no way we can approximate it with polynomial. But if we increase order of the expansion, you just see, well, 6 is the largest, we approximated beta and beta in some window. And if we have, for example, a ground state, then this construction, I don't see it, it was proposed by Matt Hastings some time ago. You can find a function which is basically equal to 0, almost 0, below some gap, and then behaves like this. And it's not exactly polynomial, but it's some combination of polynomials. So if we have a gap, that's fine, because states, say, below 2, they just don't contribute. We have a finite gap. And that's why this adiabatic gauge potential for ground states, for gap systems, is well defined. It's a local operator, so we can dress everything and so on. But if we deal, in high energies, everything decays exponentially. Because matrix element, if we deal with local operators, they're just exponentially small, so it's not really important. So, but now if we deal with in the chaotic systems in the middle of the spectrum, this is basically a window we cannot address. So, but this defines an energy shell. So in this way, we are finding adiabatic transformations between energy shells. So we just eliminate UV physics. But in many cases, that's really what we want. So one famous example, of course, is the renormalization group, which I mentioned. So this is an example how this procedure works. So this is now a specific Hamiltonian. It's non-integrable. It has some relatively generic parameters. So say J is 1. It's not shown. H is 0.3, some random number. And then we try to turn on magnetic field. And we see how well this procedure works. So as a figure of merit, we look either in the norm of this almost conservative operator or norm of the commutator with Hamiltonian. So if it's 0, then we get perfect result. If it's not, then it's not perfect. And then we see if we increase order of the expansion, we kind of rapidly go to 0. Here we saturate rapidly to its plateau. So it works very well. Okay, so now this was actually an introduction. So now I'll go to this work which we recently did and which is still unpublished, which we found quite a few surprises. This is already rich enough. So imagine that we have some 2-component field, which will be magnetic field in my case. And then I have 2 gauge potentials. So I can adiabatically transform states along one direction and adiabatically along the other direction. So, and then these components basically define this adiabatic flow, how I transform along direction 1 and 2. So, and I want to highlight the results which I'm going to present next, and they were extremely surprising to us. So there is extremely high anisotropy of the adiabatic gauge potential. So you might think, well, ergodic system, everything is a mess, so it doesn't really matter whether I go left or go to the right. But it turns out this is hugely anisotropic mass. And this anisotropy, in some sense, we cannot make statements about thermodynamic limit, but it becomes big if we find beta and beta approximations for gauge potentials. So it basically means that our landscape is extremely anisotropic in the sense that some directions are very rough, so you just move there and you excite a lot, so you cannot really connect adiabatically states. And some directions are not rough, they're very nice. So because of this high asymmetry, which might be infinite and might be very large, but if it's large, we don't know what number controls it, because it just becomes 100 when all parameters of the order of 1. Then we can define adiabatic flows connecting Hilbert spaces. So we can basically say, well, I'll show you the picture, that if we want to start from some simple Hamiltonian, say non-interacting, and turn on interaction, and this interaction, say, is 2 couplings, 2-dimensional, we have 2 different couplings, then we should follow certain directions to be adiabatic, not other directions. And then we also found that we can have another possibility, that this gauge potential is singular but still few body. So the singular part is local. And then we have very special states, if you want dark states or immune states, which are not excited. So, and these states, yeah, very interesting. So I'll stick to a model, so we don't really understand how general these results are, so there could be some other possibilities we couldn't think about. But this is the same model I mentioned. It's sufficiently generic. And I switched to notations which were suggested by Marine. I think they are much more explanatory. So ZZ will mean that I have nearest neighbor ZZ couplings. If I have Z identity Z, it means that I have next nearest neighbor couplings and so on. And everything here is translation invariant, at least in this work. So let me discuss this model a little bit. So it has some trivial regimes. So if my magnetic field is very strong, it's just non-interacting model. It's very simple. But it has other simple, if you want, points. When Hx is equal to 0, it's what people call classicalizing model. It's a model which has no dynamics whatsoever. And if Hz is equal to 0, that's another simple model. It's transverse field Ising model, so it's free fermions. So it's also like very simple. We can solve it. Now I am talking about all states, but in particular there are states near the edges of the spectrum. We usually discuss ground states, but for me ground and most excited are kind of the same. And then you can define normal sort of phase diagram. So when Hx and Hz are large, so this normal is a ground state, or so zero temperature, negative zero temperature. Think about this. So the states are disordered. It's like normal paramagnets. Now, if I go to small Hz and small Hx, then, well, this is either ferromagnetic or antiferromagnetic, again, depending on the sign of the coupling, or whether I look into excited or not excited state, and I will get an ordered phase. And then I will have transitions everywhere.
Yes, it only has the Z2 symmetry at Hz equals 0. I only know about the phase transitions on the Hz 0 axis.
But it's still, I think about this, you cannot, I understand, but...
There's no phase transition over here.
No, if you think, well, think about this as antiferromagnetic coupling, and then you slowly turn Hz. So at some point you should be... If it's antiferromagnetic coupling, yeah, it's true. Right, but then I'm just saying... No, if you look into negative zero temperature. That's what I'm saying. So for me, it doesn't really matter, right? It's true. So if you look into zero temperature, only half of the... Right.
One of the two limits that has a phase transition.
Yes, good. But then there is also a very interesting set of points for us, is that if we look into this classical model and Hz is any rational number, then this model has infinitely many degeneracies. And this is because I can find like exact number of spin flips which will sort of be commensurate with this coupling. So I can find many of them. And this will become like important. So the strongest degeneracy is when Hz equals 2. I flip one spin by 2, and I can produce 2 domain walls. So now this is one of the older results by Shaw, and sorry, notations are a bit rough, but we are still... There is no draft yet, so we'll have nice. But it shows kind of the idea. So this is sort of same parameter which I showed before. It's J's interaction is always 1 here. So H is kind of small, but not too small. It's 0.3. And then there is some angle between X and Z plane, which is, I don't know, pi over 3. I don't know why Shaw chose this particular one. I guess it was a random choice. And then we can ask how this norm of gauge potential, so norm of this Hamiltonian which defines the adiabatic transformation, changes with the order of the expansion. And then, well, it's a tensor norm, right? So we can find minimal direction, minimal norm direction, and maximal norm direction. And we see that in minimal norm direction, it basically doesn't change, which really means that I have local, well-defined Hamiltonian. I can really adiabatically transform my states very well. And then in other directions, like a mess. The more I add, the bigger the norm is. So it means that in that direction, I cannot really move adiabatically.
What
So this is size of the variational ansatz. So I told you that exact DH potential is just given by random matrix theory. Doesn't exist. But think about this. I'm interested in the limit when I take thermodynamic limit first, and then I try to find what's the best operator which addresses my states, and I increase its support more and more. So make it more and more. So here parameter is locality. So I'm becoming a bit less and less local as I move. And in this, what we call good direction, maybe we'll come up with a better term later. In this adiabatic direction, we just see that adding more terms almost doesn't change result. So it basically means my local dressing is very good. I don't want to say perfect, but it's very good. I just locally do local unitary transformations, and I follow adiabatically eigenstates. But if I go to another direction, I just see that it's getting worse and worse. So the more terms I include, the larger the norm of A. So I add more and more terms trying to follow adiabatically, and I cannot stop.
What defines the direction?
We don't know. I mean, I can say what it is for this model, but it's basically direction of this also slow operators. So there are slow operators which are slow along some directions and not as slow along other directions. So I'll mention near particular limit. So in some sense, near, say, h equals to 0, you can deduce from perturbation theory. Good directions are the states which are most robust with respect to perturbations.
So space is lambda, right? So
It's two-dimensional space, yeah.
But you know your finding point, right? It's written on top.
Well, it's the point where I start and try to shoot, like which direction. Sorry, it's a starting point, and then I'm asking which direction I can shoot. And then I see along one direction. Here, it's actually radial direction. If I move along radial direction, it's perfect. When I move along this angular direction, it's terrible.
Yeah, you mean on the field.
Well, it's for small field. I'll show you the picture, right? It changes with the field.
Radial and angular.
Oh, for field. For my parameters are hx and hz. So radial means that hx and hz change proportional to each other. Okay, so this is really the picture which I Tolle produced. So I'll try to spend some time there. It looks very nice. Really like RG. So far, we have just only hand-waving analogy. But in some sense, if you think about like randomization group, you're trying to do the same. You're trying to evaluate, eliminate UV stuff. So here we are doing the same. Because we're increasing support, we are eliminating more and more UV stuff. But we move in space of Hamiltonians. So how do we read it? So we start at the point 0, 0. So this is the most degenerate point. So my Hamiltonian is just sum of sigma z, sigma z. So you can imagine this is like a classical model. Any state with the same number of domain walls has exactly the same energy. So it's like hugely degenerate space. And then we can start shooting. So let's look into the purple curve so far. We start shooting into different directions. And then we ask, what's the direction of minimal norm of A? What is the most adiabatic? And for A, we just use 3 spin ansatz. So it's like minimal interesting ansatz. So we include in our A, which is with basic rotation, we include terms with support up to 3. And then we find something interesting. So if we start with a big angle, so hx is large, we just go all the way to infinity. This is basically non-interacting point. It's sort of spherical representation of this manifold. So nothing happens. But if we start going parallel to z-axis, we follow radially for a while, but then this is singularity at 2, which will terminate there. It's again infinite temperature diagram, and then we see this phase structure. So basically, adiabatically, we cannot really connect these two regions. They're disconnected in some sense. So the only way to do is to move here and then move back. So now we go to 4-body ansatz. So I think maximum is 6, and it's not shown here, but you kind of see the idea. So if we look into this 4-body ansatz, so we basically make our approximation a little bit better, we see that certain features of this diagram become robust. So basically the lines which were far from singularities are not affected. But if we try to go along z-axis, so basically close to these rational points, we start to see there is another singularity which develops. And this is another massively degenerate point. So in the sixth order, I think Schroeder just checked, at 2/3 we'll get another singularity. So we have like extremely fractal structure here, which basically tells us that we just cannot adiabatically move along this line. We'll generate lots of excitations. But if you want to move, as I said, with a big angle, maybe there is a critical angle, just so finite size numerics, we don't know. Then you move adiabatically for all states. So, right. Yes, and then what I'm not showing here is that if you look into orthogonal, what we call bed directions, then basically convergence is extremely, well, I actually showed it already, yeah. So you find, so this is, it might be a genuine phase diagram in the sense that we see if we increase ansatz, then isotropy between bed and God directions only increases, and we don't see bound. So maybe it's bounded, but who knows?
Sorry, I'm not understanding the notation in the diagram. Could you just
Oh.
explain again?
So these are really lines, so you shoot from this degenerate point in some angle, and then it turns out that their good directions, what we call, they're also degenerate. So any direction is good. So you can basically, there are no divergences whatsoever. And then you ask, you move a little bit, so you just change your Hamiltonian a little bit, and then you shoot again. You ask, what's the new good direction, and so on, and you follow this line. I'm sure there is a name for this, but I'm very illiterate. Right, and then you can ask where you end up. So if you move here, you go all the way to non-interacting point. So you just have a smooth adiabatic transformations of all the states. But if you move here, you end up in singularity and you cannot move further. Just not this way. So it turns out that the singularities which appear here are very interesting. So in particular, we can develop perturbation theory for this gauge potential around the special limits. They're not just non-interacting. There are limits when H0 is sum of commuting terms. There are good reasons. So this is special states, which Hamiltonians, which are very important. And then we can basically say that our generator will be like usual perturbation theory will be, say, Hx independent term plus Hx times something and so on. And then, well, here in this equation which I wrote before, in the leading order we only have H0, and next order it will be H1 and so on. So it turns out that for these special H0s, which are sum of commuting terms, we can really close, we can solve it. And in this case, the solution it's exact. It's, well, you don't even need variational on that. So you can just really plug it in and solve. And you see that basically this algebra closes if our A contains Y. This is just single spin rotation. It has to be there. But it also contains these interactions YZ and ZYZ. And then if we look carefully, then in the leading order of perturbation theory, there is indeed singularity when HZ is 2 or minus 2. It's symmetric. So we can ask what they are. And then if we look carefully into these expressions, we see that the singular part of this gauge potential is what's called this PYP Hamiltonian. Projector, sigma y projector. And projector is nothing but 1 minus sigma z. It projects to a down state, so it eliminates up state. Right? And this makes a lot of sense. Though this Hamiltonian really appeared in the context of scars, but this is so far the only connection. We cannot relate it more. But I just want to show that this is basically a singular part of gauge potential, which makes your adiabatic transformation bad. It diverges. It's infinite. But what if we start from states which are zeros, could be eigenstates, but say zeros of this guy? Turns out there are infinitely many of these states. And this states is basically when two down spins are never separated by distance 2. So we can have, for example, up, up, down, up, 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 down, and so on. But we cannot have down, up, down. And these are precisely states which you could guess right away. These are not resonant states. So it kind of makes sense that these are the special states. And for these states, there is no divergence in A. I just wrote this expression again for the moving Hamiltonian. So if we move with some velocity, this Galilean term, gauge potential term, is what leads to excitations. And if it's huge, there is no way we can be adiabatic. We just excite the system. But for this particular state, it's actually not huge, it's small. Singular part is killed by this, singular part of A kills this state, and the other things are non-singular. And this is indeed, again, I apologize for the quality of the plot, so this is still in the works. But I think I can sort of explain what's going on. So this is when we are trying to do ramp from hz equals to 2, hx equals to 0. This is exactly one of the singular points in this three-dimensional plot, moving vertically to, say, 0.52. And then if we start from 1, 0, 1, 0, it's extremely bad state. Then, well, this is energy variance as a figure of merit, how much energy variance we create. Doesn't matter what's top, what's bottom. Let's look at the bottom. So, and we see that if we increase hx more and more, we have more and more energy variance in our states. But then if we look, so this is, basically we cannot prepare eigenstate like this. Then we look into random state, it's better, but it's still bad. Why it's better? Well, because there are more kind of good regions, just randomly. But if we start from one of the states, so this is 1 is up, 0 is down, so 1, 0, 0, 1, 0, 0, 0. So, or we start from most ordered state, which satisfies this 1, 1, 0, 0, 1, 1, 0, 0. Then we see that energy variance is tiny if we increase ansatz size. So we basically can adiabatically address the states with no problems.
What are the different phase?
Oh, so this is support. This is ansatz size. So we variationally evolve them with this gauge potential. Sorry, we evolve them with variational gauge potential, and this is again support. So we make it less and less local, and we see that if we start from this good state, we basically create no energy variance. So which means that we prepare the states extremely well. So after evolution, we almost have an eigenstate. There is a little bit of energy variance, but very little. So this is like a mini summary, and then I'll mention some other stuff which I think is nice. So we so far found 3 distinct possibilities. Maybe there are more. So we have larger non-local adiabatic gauge potential. Basically means that we have badly convergent adiabatic transformations. We have large dissipation. Well, say if we do experiments, that's what we'll see. We have bad eigenstate preparation, bad annealing direction if you think about quantum annealing, bad in of motion, so we cannot get slow operators starting from this conjugates to these directions and so on. We can have small local, at least the same. And then we found there is this interesting possibility, which I just mentioned, that we have large gauge potential, but singular part is local. And then we have the subset of special dark states and so on. And by the way, we have ongoing work for some NV centers. These are real dark states in the sense of quantum optics, so they can be found in this way. So it's choice of name is not coincidental. So, and one of these things we didn't explore, in some sense with this, we can find what's the closest integrable or non-interacting point by following a good adiabatic direction. Good. So I still have 10 minutes, right? According 5. Let me just briefly mention another application of this. It's basically Schiffer-Wolf transformation. It's another work in progress with Jonathan Wurtz. Graduating is really excellent, and yeah, he developed this project basically starting from scratch. It was I'm reporting his ideas, and also Peter Klaes was involved. So just usual, the idea of the Schiffer-Wolf transformations, we start from some degenerate subspaces, or almost degenerate. We turn on perturbation, and then we split degeneracy. And the idea that we kind of try to focus on the relevant energy window, and then we have smaller Hilbert space, we can do simulations or whatever. So it's basically we start from, so the procedure, what we applied is sort of generalization of Schiffer-Wolf transformation, except that we are doing this variationally. So we start from some highly degenerate Hamiltonians, then approximately block diagonalized Hamiltonian. Again, we are kind of, we are making it block diagonal, separating, removing UV couplings if you want. And then evolve the system with the effective Hamiltonian. So it's most seen in the picture. Suppose we have a quench. We start from some state psi. Then we evolve it with some Hamiltonian, get psi of t. But that's difficult. But then, if we have, of course, some conditions, we can first do basis rotation, rotating everything, states, Hamiltonians, and so on. Then truncate our Hamiltonian, just block diagonalize. and then go back. And it turns out that this could be much more efficient.